Let us continue our discussion on overview of experimental stress analysis. How do you measure the change in resistance? And in your high school physics, you would have seen about use of Wheatstone bridge. It is a very popular and simple yet robust method of measuring small changes in the resistance. And what you have here, I have 4 arms of the bridge. I have arm AB, BC, CD and DA. And what I do is I supply voltage between the points A and C, and I measure what is the potential difference in points B and D. That is what I measure. And in your earlier class, you would have also seen how to find out the voltage AB and voltage AD, and these are given as these expressions, but our focus is different. Our focus is what happens when the resistance changes slightly. And whenever I do any instrumentation, I initially balance the bridge, and while balancing the bridge, I essentially make E equal to 0, that is VBD equal to 0. That gives me an expression VBD as R1 R3 minus R2 R4 divided by R1 plus R2 into R3 plus R4 into P. When I make E equal to 0, this gives me a condition R1 R3 should be equal to R2 R4. So, when I construct a Wheatstone bridge, I need to maintain this relationship. What should be the individual values of R1, R3, R2, R4, which would give me a optimal response of the Wheatstone bridge? I would like to have an optimal response, because I am measuring very small quantity. So, I must also look for every single effort to maximize the signal. And if I have to maximize the signal, I should understand how a Wheatstone bridge functions, and I should also bring in my understanding of solid mechanics in strain gauge instrumentation. So, the first condition shows when the bridge is initially balanced, I get an interrelationship between the resistances. So, we will see further what way R1, R3, R2, R4 should be by looking at the performance of the bridge. What we have seen, when I put a strain gauge as one of the arms, under the application of the load, the resistance of the strain gauge will change slightly. And what you have here, the expression is, suppose I have 4 strain gauges connected and each one is measuring the respective strain, there would be changes in R1, R2, R3, R4, which would be measured as delta E, and you have this expression as delta E equal to V into R1 R2 divided by R1 plus R2 squared delta R1 by R1 minus delta R2 by R2 plus delta R3 by R3 minus delta R4 by R4. What you will have to keep in mind here is, I have labeled it in a cyclical fashion R1, R2, R3, R4. This sequence has to be maintained in this expression also. And what I find here, mathematically I see a minus sign and plus sign, but how we will look at is R1 and R2 are adjacent arms, and I have a minus sign in between. What way we will look at is similar strains in adjacent arms cancel each other. So, this is one of the principle used when I want to remove the thermal influence. And what you find, R1 and R3, they are opposite arms. Opposite arms add each other. That is how we look at this expression from solid mechanics point of view, and this if you want to maximize, I can make this minus to positive if I have opposite strains on adjacent arms. I can make this quantity equal to 4. So, that way I will amplify my signal. So, the idea is you are measuring very small quantity and we should always look for ways to increase the signal output. This is also one of the requirement, particularly in transducer design, they would have this bridge factor as 4. So, now we look at the performance of the bridge. So, before we go into that, we look at what are the strain measurement options and then we will go and optimize the bridge. What way we can do? I can measure the change in EMF directly and relate it to strain, and this is useful for both static and dynamic strain measurements, absolutely no difficulty. But for me to do that, the bridge has to be initially balanced before making any strain measurement. So, this is very important. So, initial balance of the bridge is a very important criteria, and this becomes very significant when I have thousands of channels. I must have electronics and multiplexing type of situation where I am able to balance and then start doing my measurement. So, that is where the instrumentation is now focusing on. The other approach is adjust the resistive balance of the bridge such that delta equal to 0, but it is slow, it will take some finite time for you to do. This is good for static experiments, but it can provide higher accuracy. Nevertheless, for both static and dynamic cases, direct measurement of delta is convenient from practical viewpoint, and that is what we will try to do. So, now we will go and look at how I can improve the signal from my Wheatstone bridge. So, I have the bridge sensitivity, it is a function of magnitude of bridge voltage, gauge factor Sg, bridge factor N, and the ratio of resistance R2 by R1. See, what we want to look at is your initial balance only gave me a condition between the resistance. Now, I will find out for maximum sensitivity what should be the value of the ratio R2 by R1, and we write this expression delta E in a much convenient fashion. I have this as V into R1 R2 divided by R1 plus R2 squared, and the long expression is replaced by N, which I call it as a bridge factor, and you are essentially measuring delta R by R, and delta R by R can be replaced by Sg into epsilon. So, if I have to maximize my delta E, one can also say I will have a very large value of Sg. This is one of the focus in semiconductor gauges, but if I want to measure strain both in elastic and plastic regions without altering the instrumentation, we have seen it is desirable that gauge factor is around 2. So, most of the problems, whatever the strain gauge that you have, you will find the gauge factor is around 2.1, that is how you will have it. And so, we will not have much change in the value of Sg when you are using the metal foil strain gauges. I can play with maximizing m by 1 plus m squared and n, and I can also look at what way I can change the voltage. So, you should know the relative parameters that we can modify to improve the bridge sensitivity. And if you look at the current capacity is very small, we are only sending 0.1 ampere, and then the voltage that you are going to energize the bridge is only between 3 to 5 volts. You are not supplying a very high voltage. So, it is a very small voltage. So, now what I will have to do is, with these constraints I must maximize this term m by 1 plus m whole square. So, if I look at its variation, how does it appear? So, what I have here is, for constant voltage and bridge factor n and the gauge factor S g, you find the ratio m by 1 plus m whole squared reaches a value of 0.25 when m equal to 1. So, what does it translate to? You want 4 arms of the bridge to have equal magnitude of resistances. So, that is how we will construct a Wheatstone bridge. And we also have configuration where I will just use only one strain gauge, or I use 2 strain gauges, or I use 4 strain gauges. That is how I will make the bridge, depending on the requirement. So, when I do that, I will be essentially playing with the factor n. So, if you want to have a better sensitivity for the bridge, ensure that each arm of the bridge has same resistance to start with. Now, we look at what is a bridge factor. It is a very simple one. I have a single strain gauge connected, and when I do this, only one arm of the bridge is connected to the strain gauge, and from our earlier understanding, what these resistance should be? They should be equal to the strain gauge resistance. Never forget that, because you may have a strain gauge meter which has a provision to connect default 120 ohms or 350 ohms. Maybe with the modern development you may also have selection for 500 ohms and 1000 ohms. If the bridge is configured for a particular strain gauge, you must ensure that you put the balance resistance equal to the strain gauge resistance. You should not miss this fact, then your calibration everything will not match for the strain meter. And another caution is, connecting only one strain gauge poses lot of difficulties. So, it is better to avoid a quarter bridge configuration from minimizing the role of thermal influence. See, you will have to look at each aspect has to be looked at very closely and find out how you can improve the sensitivity, what are the kind of errors that come. So, that understanding is very much needed. When I have only one strain gauge, what happens? The bridge factor is only 1, and this is good enough for strain measurement, but when I go for transducer application, I always go for a full bridge for me to find out the maximum signal, and here I have it for a bridge factor 2, and you bring in your understanding of solid mechanics here. What is done here? Suppose I connect strain gauges on the top surface and bottom surface to opposite arms, what would happen? For any load I will have 0 strain. You should not think that my strain meter has gone bad, it is not so. It is how you have connected the strain gauge to the Wheatstone bridge. It is also equally important. See, in a strain gauge instrumentation, how do you pace the strain gauge, how they are connected in a Wheatstone bridge, both are important. See, in most of the strain measurement scenario, what do? You decide that this is the critical location. So, I invariably put a one single strain gauge and connect it to my Wheatstone bridge. you may essentially use a quarter bridge. Only in situations where the signal is so low you want to amplify, you may find out methodologies to amplify the signal. And suppose one such application, you have put two strain gauges on the top of the cantilever and bottom of the cantilever. You know from solid mechanics, for the kind of loading that is applied, the top fiber is subjected to tension and bottom fiber is subjected to compression, and you connect them appropriately on the Wheatstone bridge. So, here the focus is more on amplifying the strain signal, and this also has an advantage that whatever the thermal induced apparent strain in this gauge is cancelled by the thermal strain introduced in this gauge. So, you have a better thermal management when you have a half bridge, but you may not be able to use a half bridge in many of your applications. In transducer application, yes, in strain measurement application it may not happen. So, you will have to find out what application you are looking at, how you can manage the thermal influence. So, we want to find out in plane strain, and I need 3 components of strains to be determined. And now here only you look at strain is a tensor of rank 2 and you bring in the tensorial transformation law. So, what I have? I need to find out 3 components of strain. So, I need to have 3 strain gauges oriented at angles A, theta B and theta C. And you have to bring back your old memories. How do you write strain along a given direction in terms of the tensorial components? And that is a very famous expression that you have. You can take a minute to recall that expression and try to write. See, strain tensor and stress tensor share commonality. The tensorial transformation law is similar, and if you know how to write this transformation law, your rosette analysis becomes child's play. It is not no longer Greek and Latin, because there the angles are well known. You are not taking arbitrary angles, you take certain fixed angles. So, finding out how to get the strain at a point using a rosette becomes very simple if you know the strain transformation law. I think some of you have written it, and the strain transformation law is very simple. That is what you have here. I can write it as epsilon j equal to epsilon xx cos squared theta j plus epsilon yy sin squared theta j plus gamma xy sin theta j cos theta j. I have written the engineering shear strain component. If you write it in terms of tensorial components, it is epsilon xy divided by 2. And when I go to different rosettes, the theta j will change. That is all the difference. So, what I do? I get strain from this expression, and if I use the elastic constants, I can also get the stress information. And the theta measurement becomes very critical. That is the reason why you have pre-aligned strain gauges. They are mounted on a single carrier and they are called by a special name called rosettes, and you need these strain gauge rosettes for finding out the strain tensor at a point of interest, The greatest advantage is they are pre-aligned, and because you are having a metal foil, it is easy to do this very precisely. And I have always been saying the basic information given by an experimental technique is dictated by the physics that we exploit. So, in a strain gauge, you essentially employ change of stress modifies the resistance of the conductor, and I essentially measure a component of strain. Once I measure the component of strain, if I know the elastic constants of the base material, it is possible for me to find out the stress on the specimen by invoking equations from mechanics of solids. And let us see two famous configurations of the rosettes. And one of the rosettes is called a rectangular rosette. It is primarily because I have a strain gauge along the x axis, and the second strain gauge at 45 degrees, and the third strain gauge is along the y axis. So, what is the strain measured by the strain gauge A? If I have this as my reference axis, I could simply say it is equal to epsilon x, and strain measured by the strain gauge C is epsilon y. So, now you use this strain transformation law and find out what is the shear strain. So, I will have epsilon A, epsilon B, epsilon C measured from the actual strain gauge, use it and find out what is the state of strain at a point. Then we moved on to how to measure the change of resistance. We said Wheatstone bridge is the most celebrated type of measuring approach. Then we looked at what is the accuracy achievable in strain gauge instrumentation, and finally, we had a brief discussion on how do you find out state of strain at a point, and we have also seen what is a rosette. And as an exercise, I would like you to get the shear strain in the rectangular rosette which we have seen. Thank you.